In this video, we will see different kinds of tests, how to perform that using Graphpad Prism 8. Independent t-test and Mann-Whitney u-test, pair t-test and Wilcoxon matched pairs signed rank test, one-way ANOVA and Kruskal-Wallis test, two-way ANOVA and two-way ANOVA with repeated measures, also known as repeated measures ANOVA. So let us go back to the same example file of the Graphpad Prism that we are looking at. So on the left panel, choose independent t-test. So the same test that we have described that in our class. So it is old and young rats of the bladder muscle relaxation data here. So this is the two groups. So how to perform the the t-test, the independent. So as you see, this is independent and this is nothing matched, right? These are different rats, old rats and the young rats. And as you can see, the sample size is also unequal, so definitely it's not matched. Let us click here, analyze, and of course the column test. So it is a t-test and non-parametric. So I click here, old and young, click OK. So is it unpaired or paired? So it is, there is nothing pairing here, so it is unpaired, it's absolutely fine. And parametric is fine. And assume that both populations have the same ST. So Welch correction, do not assume that the equal ST. So it is the first one is always better. So let us go with this unpaired with all default options. Click OK. So you will see that this is the data that you're going to get it. So how will you see that this data, independent t-test, young versus old, fine. P-value is 0.003, which is less than our threshold 0.05. So the value summary, you can see the 2 stars, so it is significant. Is it significantly different at P less than 0.05? Yes, and it is a two-tailed, and this is a t-score with degree of freedom is 15, so because the size is n. Now, how big is the difference? 30 and 53, and the difference between the mean is 23.55 plus or minus 6, and the confidence interval, as you can see, 9.3 to 37.7, which does not include 0, of course, so that is why it's significant. And R square also you can see. F test to compare the variance, as you can see, it is non-significant. That means it is of the same variance, and this is the data analyzed. So that is the summary of the independent data. So we can also do the same thing using a non-parametric test called Mann-Whitney. The procedure is exactly same. Analyze for the t-test and non-parametric. I click OK. So analyze this table once again. I click OK. And then this here you can see no, use non-parametric. There are two options, Mann-Whitney or Kolmogorov-Smirnov test. So if it is for the cumulative distribution, but here it is rank based. So let us go, you can choose both, either of these options. So let us go with the Mann-Whitney test. I click OK. So as you see, the Mann-Whitney p-value is 0.0035, which is quite similar to our independent t-test. It is an exact p-value. The p-value summary is double star. And significantly different, yes, it is significantly different, which is a two-tailed test, Mann-Whitney u-test. So the difference between the medians also, you can see that for the, as you know, the Mann-Whitney t-test works at the median level. So this is also a very convenient way to do a Mann-Whitney u-test using a Graphpad Prism. Now let us go with the second data table, the paired t-test. So this is what the pair t-test looks like. So for the pair t-test, the cross-fertilized and self-fertilized, and this is a matched one. This is also the same example that we used for this is a Darwin's, the example. And for this, the cross-fertilized and self-fertilized thing for the matched group, it's always better to go with the before and after plot. So how to do this before and after plot? So it's a very simple new graph for the existing data, and we can go with before and after plot. So here you can see that there are several things. Here is a before and after is coming up default, and I click here OK. So as you see that most of the data is actually reducing cross-fertilized to self-fertilized, and this is nothing but height. So height is reduced, so I can actually click and add it here, heights. right? So heights are being reduced when the cross-fertilized and self-fertilized of the same pot. But only two readings are increased in the self-fertilized having more height than the cross-fertilized. So this is a very easy way to generate the before and after plot in the Graphpad Prism software. So after inspecting it, now let us go with the pair t-test for this one, as well as the Wilcoxon matched pair sign rank test. So it is very simple, quite identical. So I click here t-test, okay, and unpaired or paired. So in this case, we have to go with paired and parametric test, right? I click OK. The result is presented here. The paired t-test p-value is 0.0497. Yes, it is significant, but you see it is very borderline case. We can also inspect the 95% confidence interval. Both are minus, doesn't include 0, but you see the upper limit here is 0.00020 zeros and 3, which is very near to 0. So it is very borderline case. So this is the summary of this pair t-test. So instead of pair t-test, let's go with the this one Wilcoxon test as well. Analyze t-test. I click OK, and let us reanalyze. And this is of course the paired. And let us go with this time non-parametric test, that is Wilcoxon matched pair sign rank test. I click OK. So it takes some time because there is a lot of computational iteration. This is a non-parametric test. Now, as you can see, the p-value, exact p-value is 0.0414, so which is very near to close to 0.05. And you see the independent t-test, the dependent t-test, and Wilcoxon matched pair sign rank test, the p-value is quite identical. It is significantly different, but it's quite borderline case. And as you see that one issue with this sort of non-parametric test is that it does not produce the 95% confidence interval, unlike the parametric test. So there is only issue with that, but otherwise the p-value is quite comparable. Now let us go with one-way ANOVA, the same data that we used earlier. Uranium, lead, arsenic, and mercury. And of course, these are independent measurement. There is no paired, matched pair. So let us go with the one-way ANOVA. Click Analyze, and I click here one-way ANOVA. Okay. So there is no, of course, there is no matching. And use ANOVA. Or you would like to go with non-parametric, of course, ANOVA is fine. Would you like to go with ordinary ANOVA or, so corrected ANOVA? Let us go first with the ordinary ANOVA. So there is no point in going for repeated measures. And let us go with multiple comparison. Yes. So if you're interested to go with, of course, the usual ANOVA doesn't make any sense unless you have to go with the appropriate post hoc test. So let us go with multiple ANOVA. The option is that Tukey's test for multiple ANOVA. And let us also produce a graph for the confidence interval of the Tukey's. We have explained all these formalities, how to interpret this graph in the module. If you haven't watched, I suggest you to go and watch the module first. Then I click OK. So as you see, this is the ANOVA result. So ANOVA result is that p-value is less than 0.0001 and the F is quite high, so it is significant, and now you can see that this is the ANOVA table and the p-value is very less, and mean square, degree of freedom, sum of square, everything is here. And now let us go with the multiple comparison. Here you can see the uranium versus lead. Is it significant? Yes. Arsenic is significant? Yes. And the third one is also significant, but the fourth one is summary is only 1 star. That means that the adjusted p-value is quite high. That is why it is only 1 star. So it is lead versus arsenic. But lead versus mercury as well as arsenic versus mercury, there is no significance here. And this is a very good way to see that this is actually the Tukey's honestly signified difference. Now let us go scroll down to see that multiplicity adjusted CI plot. So this plot is what it is. So the two things, arsenic versus mercury and lead versus mercury. This is the 95% CI of the difference. As I told you, the 95% confidence interval of the difference, if it includes the no difference, that is our null hypothesis of 0, that means it is not significant. So that is why these two values are not significant, while these four values are significant in Tukey's test. So this graph is a very easy way to understand, interpret the Tukey's results in it. So now let us go with the next one is called two-way ANOVA without any repeated measures. So here you see that the pH 5.5, 6.5 and 7.5, these are culture media grown at different pH, and these are at different temperatures, you know. So these are nothing but technical replicates 9 and 11. This is the colony founded. So now to do this into ANOVA, all you have to do is same way analysis. It is a two-way ANOVA with all the three columns. I click OK. So of course this is not RM, and we will also go with multiple comparisons. Compare row means main effect. Options will be the same Tukey's, and I click OK. So as you can see that the ANOVA here is that interaction, it's a two-way, because that is why it's a two-way, the interaction is very high, so it is significant interaction. Rho factor here is that rho factor is nothing but the rho is temperature, there is no significant differences, while column factor is the pH. There is significant difference in column factor, so this is what we could find it. This is the ANOVA summary table. Now if you click on the tab multiple comparison, you can see that none of the row factors have got significant result here. Nothing is significant. So adjusted p-values, you can see all are higher than 0.05 cutoff. So that way you can interpret this two-way ANOVA. Now let us go back to the first one, the one-way ANOVA. Here there is another way to do the same test. You can use Kruskal-Wallis test also. How to do that? Click on Analyze, one-way ANOVA, non-parametric. So we'll go with non-parametric this time. Analyze this table once again. I click OK. So instead of ANOVA, I go with non-parametric test, which is nothing but Kruskal-Wallis test. I click OK. So this is what you're going to get. For the Kruskal-Wallis p-value is significant, just like our one-way ANOVA exact p-value, which is less than 0.0001. So this is what the Kruskal-Wallis says. So this is how to perform Kruskal-Wallis test using Graphpad Prism. So this is, let us go with the third option, that is the two-way ANOVA with RM. So RM is nothing but repeated measures. So wild type, tame and raging wild, these are different genotypes, and these are nothing but before and after, with technical replicates. So we have for repeated measures. So this each one makes sense here. This is a wild type genotype before and after the treatment. So in this case we'll have to go with RM by rows. So we'll go with Analyze, two-way, click OK. And as you can see here, matching. So matching, each column represent different time points. So there's the first option is absolutely fine. So and then RM analysis option. So you can see that this is absolutely fine with that. And multiple comparison, if you would like to go with multiple comparison, you can also go with that. Compare row means with the main effect, and the options could be Tukey. And I click OK. So in this case, it will show you two-way, what is basically the thing. In this case, interaction is, interaction p-value is 0.01, which is borderline significant, while row factor is not significant. Column factor is significant. So these three things are very important to see your, the two-way ANOVA interaction ANOVA results. So you can also check out the multiple comparison of the Tukey's wild type versus tame Is it significant? Nothing is basically significant. That just if p-values are more than 0.05. So that way you can perform the repeated measures ANOVA in Graphpad Prism. Thank you for watching.